Relationships involving heat of reaction. So if we look at this reaction, carbon reacting with oxygen forms CO2. The heat of reaction for this is minus 93.5 kilojoules. Well, if we had twice as much, if we had 2 moles of carbon, 2 moles of oxygen, and made 2 moles of CO2, it should release twice as much energy, right? So if we multiply the coefficients in the chemical equation by a factor, then we also have to multiply delta H by the same factor. If we made all of these 3, we'd have to multiply this by 3. That's reasonable, right? If we reverse the reaction, instead of saying that we're forming carbon dioxide, we're decomposing carbon dioxide back into its elements, well, energy must be conserved. If you run the reaction forward, we're releasing energy. If you run it backwards, you're absorbing energy. It's the same amount of energy. Does that make sense? So I sell you something for $10. You give me $10. We reverse the transaction. You give the object back. I give the $10 back. It's the same amount of money changing hands. It's just going different directions. So this is just the opposite process. So we just change the sign of delta H. You reverse the reaction, you reverse the sign on delta H. And this is a concept called Hess's Law. If you can express the reaction as a series of steps, this reacts to make this, and then that thing reacts to form this other thing, and then here's the overall reaction. So in this example, what do we have here? We have A plus 2B is forming C. So that's this one right here. And then C is forming 2D. So we have a delta H for this, and we have a delta H for that. Well, we did this with half reactions. We can add chemical equations. So if we add these two reactions, the C that's produced here gets used up there, and so my overall reaction is A plus 2B makes 2D. Well, if this is the energy change for the first reaction, and this is the energy change for the second reaction, then the overall energy change must be the sum of the delta H's, right? So delta H for the overall reaction just equals delta H1 plus delta H2. Does that make sense? So let's go back to our mountain analogy. It does not look like a pile of something. So let's say there was this base camp. So up here was 10,000 feet elevation. And down here is 0, and this is 5,000. And so you hiked up here, and then you broke your leg, and so the helicopter came in and carried you the rest of the way, right? So the first leg of your journey, your change in elevation was 5,000 feet. The second part of your journey, which happened in a different way, was also 5,000 feet. What's the overall change in elevation? It's the sum of them, right? This works because delta H is a state function. It doesn't matter how you got there. It's just the difference between where you are now and where you came from. So the process, if you do multiple equations, multiple reactions, or if you do this one straight out without anything in between, the change in energy is the same regardless. Any questions? In this energy diagram, we see that this reaction is endothermic because the products are higher in energy than the reactants, so energy came in. And then this reaction is exothermic it's releasing energy. And so overall, we take this one and that one, and we add them up, and we get this difference. And we see that it is exothermic, but smaller. Any questions? Okay, let's apply those things. Find delta H, the enthalpy of heat of reaction for this reaction. We got N2O plus NO2 goes to 3 no's. Not 3 noses, 3 no's. So use these reactions with known delta H's. So reactions like this, you can go to a table in the textbook, you can go to the CRC, you can go to the internet. You can find data like this because other people have measured it and written it down for us. Hess's law allows us to estimate, this is not going to be exact, but to estimate the heat of reaction for this chemical reaction if we can find some known things that we can combine to get this. So what we're going to do is we're going to figure out how can we manipulate these 3 chemical equations so that we can add them together and make this one overall. Okay, some of you are going to think this is fun, and some of you are going to hate it with a passion. Well, how do you even approach this? There's not one correct way to do this. You could come at the correct answer several ways. What I like to do is I like to first look at what I've got going on up here, and I'm trying to get N2O and NO2 on the left side and to get NO on the right side. So I'm going to look through here, and this has NO on the right side, this has NO on the right side. I mean, this is on the left, this is on the right, and then that doesn't have any of it. So let's just maybe start with this first one. If I write this as it's written here, am I going to end up with NO on the right side? Here, NO's on the left side. So that's not going to work. What if I reverse the equation? If I write it backwards? Would that work? If I write the product first, that's not very good too. 2 NO2 gas makes 2 NO gas plus O2 gas. Then I have to switch the signs. So I took this equation and I just reversed it. When you reverse the direction of the reaction, you change the sign. So for this one, I have to change the sign from a negative to a positive. So this is closer to this. Now I have NO2 on the reactant side, and I have NO on the product side, but I also have this O2 in here, and I need to make that go away somehow. So I've got this one. I could stick this one in here, right? I could put O2 and NO on the right and help to get rid of that NO2. I'm sorry, help to get rid of the O2. There are some ways that are going to be longer than other ways, and I'm suspecting that if I do that, that's going to make it longer. So I don't have time for that in lecture, so I'm going to think again. I've got the NO2 as a reactant. I need N2O also as a reactant. This second equation doesn't have N2O, but this last one does. So I'm going to put this one in here so that I can get N2O on the left. So 2 N2O gas is going to make 2 N2 gas plus O2 gas. Did I do anything to the equation? No. I don't need to do anything to delta H. So this is going to give me 2 NO2 and 2 N2O on the left side, and it's going to give me 2 NOs on the right side. But now I've got these oxygens and the nitrogens, and I'm going to have to cancel them out somehow. So I want to use this one. So I'm going to put that one in as it's written also. Just line these up a little better. So NO on the left side, and N2 and O2 over there. And let's check this out. This N2, I can cancel out one of these, but I can't get rid of both of them. This O2 would get rid of this O2, but not the other O2. What do I need to do to this equation so it's going to get rid of all the O2s and N2s? I need to double it. So I'm going to multiply that by 2. So this is going to be 2 N2s and 2 O2s and 4. That's not very clear. And 4 NOs. If I multiply the equation by 2, what do I have to do to delta H? Multiply by 2. So I have to multiply this one by 2. So let's see how things are working out now. So I have 2 N2s there. That'll cancel the 2 N2s over there. And 2 O2s will cancel those 2 O2s. Right? So let's add these together so that we can see what we've got going on here. So I have 2 N2O gas plus 2 NO2 gas, and that's going to make, over here I've got 2 NO and 4 NO, so that's a total of 6, right? So I've got the correct reactants and products now after combining these 3 equations. How is this equation different from what I'm supposed to be finding? It's doubled. Well, let's find out what delta H for this one is. What we're going to do is we're going to add these things up. I changed that one to a negative, to a positive because I reversed this one. I'm multiplying this by 2 because I multiplied the coefficients by 2. I didn't do anything to this one. So let's find out what delta H for this one is. That's going to be 113.1 plus 2 times 182.6 plus a negative 163.2. And I'm getting 315.1 kilojoules. Yeah, so now I've got this for this reaction. I need to divide this by 2, so I'm going to divide that by 2. So we'll divide all of these by 2. That goes away, and this becomes a 3. So delta H equals 157.55 kilojoules for this reaction. N2O gas plus NO2 gas, making 3 NOs. And in terms of significant figures, this should be just right there. And so delta H for this reaction is 157.6 kilojoules. Any questions? This is one of those things that, while it doesn't sound easy, it sounds easier than it is to actually do it because it gets into this picky, all these detail things. You really have to write it out. You really do. And I guarantee you there will be a question like this on the exam.